Okay, next up we have Matthew Luckie from CAIDA.
Hi, this is work that I've done, work that's been going on for around about 8 or 10 years now at CAIDA, and what I'm talking about has been going on, the work that I've done over the past sort of year. This is work that I've done with Brad, Amog and Casey at CAIDA. Okay, so what this talk is about a project called ASes, which is available on the internet. All our results are available on the internet at asesrank.caida.org. And what this project is first we infer AS relationships, going down the same road that a number of other researchers have gone down over the years of using publicly available BGP paths. So what we do is we download ribs from route views and RIS, and there's approximately 400 ASes providing views to route views and RIS, and about a third of them are providing full views. And with the AS relationship inferences we make, customer-provider, peer-to-peer, we then try and infer the influence of individual ASes based on the size of their customer cone. And the way to think about the customer cone as an operator is traffic that arrives from a customer and then is transmitted to a customer. So essentially the fraction of traffic that makes you the most money because you're being paid twice for it on net traffic. So an overview of this talk, I'm briefly going to talk about some objectives of the work, and then most of this talk is a methodology about how we go about it in order to gauge feedback from you about the validity of our assumptions. So we're going to spend a lot of time talking about the assumptions, about how the algorithm works. I'm going to illustrate the algorithm with a sample path, and I'm going to show you some results, some graphs. And I've got a slide at the end about how you can help. So I think we can all agree that AS relationships determine how traffic flows through the internet, and having a set of accurate AS relationships enables us, supports some measurement of the infrastructure security and stability. What happens if, say, one of the larger ASes with a large customer cone is disrupted? What is going to happen in the internet in terms of reconvergence? How many paths are going to be disrupted? So on. Analysis of BGP misconfiguration, for example, the Telstra Dodo case, where Dodo starts announcing provider routes to another provider, we shouldn't see this in the internet, so having a set of accurate relationships might enable us to detect this automatically. And what we're using it for is an analysis of the influence of ASes based on the size of their customer cone. And again, it's roughly what is the absolute number of ASes that a provider could charge traffic for. So in this talk, we focus on two AS relationships. These are the canonical ones. They don't always hold, but they come pretty close. Customer-provider, where the customer pays a provider to have access to its providers, peers, and customers, and peers, where the ASes agree to exchange traffic between their customers. With these set of relationships, we assume that the cash flow follows from the customer to the provider. And in terms of BGP relationships, we can't tell if peers are settlement-free or paid peering. I'd like to have feedback on that towards the end. But essentially money is flowing from the customer to the provider. So the customer cone is given a set of relationships. For A's customers, direct customers, are B and C. But A, provided that traffic reaches it from C, will receive settlements not from D, but will be paid to transit traffic from, for example, D to F, assuming it doesn't go across the peering link. So A's customer cone contains B, C, D, and E, and F, but not G, which is across a peering link. So the customer cone contains customers as well as indirect customers. So we have a set of BGP paths on the left and a set of relationships we've inferred on the right. I'm going to present 3 different ways of constructing a customer cone and solicit your feedback on each of them. The first one is what's called a recursive customer cone. So because we infer E to be a customer of B, it might be natural to infer that E is an indirect customer of A, except the BGP paths don't suggest that that A has a path to B because we never see one. So the recursive cone contains all of the ASes in the graph, 5 of them, but if we look at what is observed in BGP paths, we don't see a path from E to A, so that follows customer-provider links, so we infer that its customer cone size is 4 and does not contain E. But the computation is a little bit more complicated than that. So ASes may have, and a piece of feedback we've had repeatedly is that ASes may have a customer-provider relationship in one region, but be pairing elsewhere. But when we assign relationships, we choose a single relationship between 2 ASes. So when we infer a customer-provider relationship, that overrides everything on the graph. So even if they're pairing nearly everywhere else, we infer a single relationship customer to provider. But using observed BGP paths limits the amount of damage that can occur. So in this example, we have X and Y with region-based relationships, customer-provider, and C and B have region-based relationships, customer-provider in America and peer-to-peer in Europe. So B's cone will contain F, G, and H using the observed cone, using observed BGP paths if we see the paths across the pairing link, because we infer customer-provider for between C and B overall. But A's cone will not. A's cone will only contain from C, D, and E, because those are what we observe to see followed on a series of customer-provider links. So a third approach to defining a customer cone might be to define it based on what we see announced to an AS's peers and providers, what we believe with great certainty to be the customers, the actual customers. So in this case, because we see a path to A from B that contains D and E, but not F, G, and H, then we will infer B's customer cone to contain just D and E and C. So with the customer cone in mind, there's a bunch of caveats. Again, I've talked about region-based relationships, and beyond that, we can't differentiate between paid pairs and settlement-free pairs. So a paid pair we do not include in the customer cone of an AS, even though they are paying settlements to their pair, even though one of the ASes is paying settlements. But the feedback that we've had in discussions with operators is that there's no routing difference, that a paid pair is treated identically to a settlement-free pair. We don't know about traffic, so if you're a large access provider and you have tens of millions of residential customers, your customer cone is going to be small because your customer cone is counted by ASes, so we don't have traffic. We don't have a lot of visibility into pairing. To see all the pairing relationships in the graph, we need ASes below the pairing link, and we don't have a lot of, again, 400 ASes, that's about 1% of all the ASes in the internet, so we don't see a lot of pairing relationships. The paths, the public data source that we use is messy, again, because of poisoning, so we might infer relationships that don't exist because of poisoning and potentially also leaking. And the size of a customer cone is not a metric of market power. We need a lot more data than customer cone to infer market power. But with these caveats in mind, and maybe to keep you interested, I'm going to present a few graphs. So this graph is the observed customer cone time series from 2002 to October 2012. On the y-axis is the size of the customer cone in ASes in absolute numbers that we've observed over time. And we see in this graph a number of ASes that have increased in size. I've labelled a few mergers. You can see on the bottom left where level 3 acquires Genuity and merges with them, and up on the top right just recently when level 3 merged with Global Crossing. So this is using observed paths, and this doesn't cleanly deal with region-based relationships. Particularly, you might notice that there are spikes in the graph that aren't well explainable. These could be due to a single relationship being misinferred, or it might be that we have visibility sometimes but not others. But perhaps it could also be due to us seeing periodically evidence of region-based relationships. So this graph is the customer cone as defined by an ASes providers and pairs. So this cone is likely to underestimate the size of an AS because we are presumably missing some customers. In fact, we know we're missing customers. But this treats all ASes equally, in fact. If you provide a view to route views, then we have a good view of your AS, and that is reflected in the observed cone. But in the provider and pair cone, that view itself does not influence the size of the customer cone. But what matters is what your peers and providers relay to us, or relay publicly. So in this level 3, the largest AS has a customer cone that in absolute terms in late 2012 is 44% of the internet. In the observed cone, the previous graph, it's 59%. So that's customer cone. I'm going to talk about the AS relationship algorithms the algorithm that we developed. We went back to the drawing board with this because in the ground truth that we'd collected over a number of years, our relationship algorithm that we provided data publicly for, and a number of other ones did not match the ground truth very well. So with that in mind, we tried to develop a new one. So I'm going to begin with a few definitions. A transit degree. So we used given a set of BGP paths, an AS's transit degree is a number of AS's for which it provides transit for. And we can't tell if the AS's that they are transiting traffic between are providers, customers, or peers. But what it allows us to do is to differentiate between large transit AS's and large edge AS's that might pair extensively. So this is instead of a node degree. So in B's case, B's transit degree is 4 because it provides transit between A, C, D, and E, but not F and G. And this is observed using BGP paths. We have an assumption that there is a clique of ASs at the top of the hierarchy. You may think of these as Tier 1 ASs, but these include more than just the Tier 1 ASs. These include other transit providers that may be paying settlements to other members of the clique, and a full pairing mesh. So we expect in our algorithm, what we are looking for is for a link between an AS and all other members of the current members of the clique, and that there is no evidence that there is transit taking place, that the transit is not being provided to an AS across the clique. Some ASs have a relationship with all of the Tier 1, all of the clique, but they receive transit from some of them. So we don't include those in the clique. The assumptions behind our algorithm are as follows: that we have that clique at the top. Otherwise, and the reason this has to exist is that otherwise internet topology is partitioned, or ASs need to have relationships with all members of the clique. We assume that a provider announces customer routes to its providers. This is the main point of paying a provider, to obtain connectivity to the rest of the internet. We assume that the transit degree of a provider is larger than that of its customer, and this is supported by our ground truth. 99% of providers are larger than their customers in terms of the links that we see, and that the topology graph in terms of provider-customer relationships is acyclic. That means we never see A as a customer of B, B as a customer of C, C as a customer of A. Existing relationship algorithms produce these things called strongly connected components, and ours does not, and this is supported in our ground truth. We see no P2C cycle in our ground truth. So a high-level algorithm is that we infer the click and the pairing mesh at the top. Then we do some filtering of our BGP paths. An example of the filtering we do is remove paths reserved to ASes, and we remove paths where there's evidence of poisoning. For example, if we see two click ASes with a non-click AS in the middle of them, that suggests that the two click ASes are using another AS as transit, but we know that they do not require this. They can exchange traffic between themselves. So we infer that's due to poisoning. Then we break our paths into triplets. In this algorithm, we are not seeking to maximize valid paths, as previous relationship algorithms have done, but we use the basic unit of information in the construction, in the paths. Then we visit ASes in top-down in order of largest transit degree. And we infer a neighbour if a customer to provider relationship if a neighbour passes a route to a provider, or if the neighbour is a member of the click and it passes the route to another member of the click. And this gets us 56% of all the observed graph relationships inferred for that, customer to provider relationships. And these are 99.8% correct according to our ground truth. There are additional steps in our algorithm, but essentially everything that we don't infer to be a customer provider is inferred to be a pair, and that's 37% of the graph, and 98% of those relationship inferences are correct. So, given a set of BGP paths, we have millions and millions and millions of these, but given just this one, we have a path involving five ASes. I've labelled two of them because we recognise these as AT&T and level 3. But to begin with, so there's a directionality to a BGP path. The route flows from the origin to the vantage point. The vantage point is providing its view to route views and RIS. We don't know anything about the relationships at this point, but we infer in a previous step that AT&T and level 3 are members of the click and have a pairing relationship in them. Then we break up the path into triplets, and then we label each node with its transit degree, what we observe to be its transit degree. So A, in terms of the transit degree, apart from the click ASes, A is then followed by C, and then is followed by B, and then followed by C by transit degree. Then we visit them in order of transit degree. So we visit A first. Now, it might be natural to infer that A is a customer of AT&T in this case, because there is a pairing relationship upstream from them. But we don't make an inference based on this information unless we have other things pointing us in that direction. Because it could be the case that AT&T is leaking pair routes to A. We would expect, if A is a customer of AT&T, that they appear on the right-hand side of AT&T in a BGP path, because then that means that AT&T is announcing paths from A to other pairs and customers. And that decision to do so has been validated multiple times, and if we don't enforce this rule, then our validation results go down. So that's essentially why we do it. We infer B as a customer of level 3 because we see level 3 announce across the click. So again, if A had appeared on the other side where B appears now, then we would have inferred a customer-provider relationship, but in this we don't. And we still might be inferring leaking, but we can't do much about that. We infer C as a customer of B because we see B announce to its provider routes from C. So, and we proceed. So we have 7% of special cases in our algorithm, vantage points with no provider routes. So, like I said, roughly 2/3 of ASes provide not a complete view. If an AS provides less than 5%, routes to less than 5% of ASes, then we infer that it's providing peers and customer routes, not provider routes. And so we have a special case to deal with customer-provider relationships below them. We have a case, of course, to deal with providers that have a smaller transit degree than their customer. We have a case to infer customers for ASes with no providers. Again, our algorithm focuses on inferring providers and not customers, but we have to do it for ASes that have no providers, because otherwise we would infer no customers for them. And a good example of that is transit rail. And finally, when all else fails, then we are left with triplets where we have inferred no relationship, and if we infer no relationship, then we will infer both links to be peers, and this may or may not be the case. So we try and collapse one of the two ASes down. We tend to bias collapsing Z down to a customer-to-provider relationship with Y. So in terms of our ground truth, our efforts to validate this, we have assembled a set of 47,000 relationships. We acquired 2,000 of them directly through AS rank from 2010 to 2012, and what these were submitted were mostly pairing relationships. Our previous algorithm inferred many more providers than existed, and when an operator or someone with knowledge would visit the page, they'd correct our false provider inferences to pairs and essentially leave everything else. So there's some motivation to do so. We used the routing RPSL database from RIPE to extract a set of customer-provider relationships. Because there might be some out-of-date relationships recorded, what we require is that they have been updated within the last 2 years, and that for each link where we have A and B, we expect to see A express that B is a provider, and in the RPSL entry for B express that A is its customer. So we have high confidence in this set of ground truth. And finally, we have a set of relationships extracted from BGP data using community values. Versedius assembled a collection of roughly 40,000 relationships that are expressed in BGP communities as defined by operators. So these are published in web pages and in WHOIS for approximately 230 ASes. And so roughly 2/3 is provider customer in our ground truth overall, 2/3 is provider customer, and a third pair. And it validates approximately 38% of the graph. In terms of how we do and how other inference algorithms do, we're very accurate inferring both provider customer and pairing relationships. 99.6% of provider customer relationships that we classify as provider customer relationships are what we say they are. So 0.4% of those are pairs. You might notice down the bottom, Gale has a very high positive predictive value for pairing relationships, but like our previous algorithm, they inferred many more providers than in reality, so they have a very small set of peer-to-peer relationships, and the small set validate well, but their provider customers don't do so well. So this is the click that we've inferred to exist over time. What we're looking for, because we don't have a good set of ground truth for who is in the click and who is not, what we're looking for is some semblance of stability. So 9 of the ASes have always been in the clicks for the past 11 years. We have seen some that have been merged, for example, down the bottom level, AS1, WorldCom went away. And more recently, there have been ASes, particularly in Europe, that appear to be in the click, because we don't see any transit relationships for them. But this might be a limitation of our BGP data, we're not sure. And what we have plotted here is a graph of the three largest ASes as they stood by customer cone in 2002, January 2002, and the three largest now. So I plotted for the third line Cogent, but Cogent looks roughly the same as IntelliQuint and what were the other ones? Oh, I'll have to see it, sorry. They look roughly the same as IntelliQuint, and there's others. Telius and Era. So we've seen from 2002 the birth of three very large ASes, in fact maybe 5 or 6, and the ones that were the largest 10 years ago are not so large based on the size of their customer cone. And level 3 has approximately 44% of all ASes in its customer cone, and that's been relatively static for the past 8 years. Again, this is our provider and peer-defined customer cone. This is what the previous graph is based off, except now we're showing absolute numbers. And again, you'll see to the right, Cogent, IntelliQuint, and Telius and Era roughly the same size, and their lines follow roughly the same pattern. If you can pick them out, I'm happy to show you this graph afterwards. So in terms of what we'd like help for from Nanog, we'd like to know what it is that we have not thought of. We'd like to have some information about how prevalent paid peering is. We've received some amount of indications of paid peering, but not enough for us to be able to come up with any methodology about how we might distinguish a paid peer from a settlement-free peer. And in fact, we're not even sure that we can do so with the BGP data. Related to this, and one of our assumptions is that a customer is announced to a provider's providers. In what situations might this not occur? We'd like to know something about how prevalent complex relationships are. So if you can provide us with ground truth information about relationships you have with ASes where they are a provider in one region but peering in another, we'd like to hear about that. We'd like to know what the granularity of complex relationships are. Is it a region-based thing? We've heard it expressed mostly in region in our feedback, but it maybe it's at prefix as well. And ideally, more vantage points at route views and RIS and additional ground truth. And with that, questions?
We do have time for questions or comments.
Jeff Houston, APNIC. In this study, you're kind of treating every AS as an AS, right? But I notice in the allocation statistics that in the Asia Pacific region, there are only 5,100 ASs that are ever allocated. Yet in North America, 15,000, and in Europe and the Middle East, 18,000. So it seems that an AS isn't an AS, and that while in some parts of the world, notably in Europe, ASs actually express a relatively fine-grained degree of routing policy, whereas in other parts of the world, ASs encompass much, much larger sets of users and policies. How does your study relate to this difference that we see in the use of ASs across the world?
It treats them all as equals, and that's a limitation. Again, we don't have traffic, which is essentially what we want. Whether or not this can be used to as a proxy, I don't know.
As a simple observation, somewhere in that massive ranking of huge providers, you would expect to see something like China Telecom, but they're phenomenally notable by their very absence in any such ranking. And it kind of wonder how you would integrate different regions' uses of ASs into this.
I guess we would need additional information and some way to express that as a rule. So we need more ground truth.
Hi, Patrick Gilmore, Akamai. Can you go to the questions slide? So you're asking questions here that, how prevalent are complex relationships, how prevalent is paid peering and things like that. There's, 40,000-ish ASs available in the global table. for 30-something thousand, 35, 39,000 of them, the answer is 0 to all of the above. So if you limit yourself to a much smaller set, then the questions become nearly 100%. The complex relationships of even the networks that you had in that slide, the very large providers, are massively complex. I mean, look at just what level 3 announces through press releases, and the fact that, Comcast got them to, somebody here who works for Cogent is going to be pissed at me now. The fact that level 3 puts out a press release saying that Comcast forced them into peering, as well as having a transit relationship and things like that. So these are all, well known as ground truths, as you say. But the problem is that you're treating everyone the same, when in reality, the very, very top ones have complex multilateral relationships. And like Jeff pointed out, BGP works on a prefix. ASes are a convenient grouping, but clearly it doesn't work that way. If you just strip out the bottom 90-something% of them and concentrate on the complex ones, you might have a better shot. But then you have to your algorithm, your procedures have to be far more flexible and complex. If you want to do just the bottom however many there are, then these things become much easier, and everything you say holds easily. Does that make sense?
Yeah.
Okay, what's the chances of you doing that on a per prefix basis for level 3? That's what I thought.
Thank you.
Let's thank the speaker.